Hello everyone, how you all doing? Today, IEEE chapter has brought to you, as Jan mentioned, a very interesting session on a topic which is not just very beneficial in terms of your career, but also is so much fun to do. Myself, Srishti Lodha, and my partner, Soham Mittal, we both are going to be taking a session. We both are second year students of Computer Science branch in VIT Vellore. So, without further ado, let's begin on the session of competitive coding. So, what is competitive coding? There is no right or wrong answer. So, any of you, if you could come ahead and tell me any idea that you have about what competitive coding is? It's a competition on programming. Correct. That's appropriately what it is. So, thank you for the answer, Nirav. Let's begin with the session. So, competitive coding. It is a mind sport. Now, what do I mean by a mind sport? We all love to play sports, right? Basketball, football, tennis. Now, mind sport is something that keeps your brain sharp and that helps exercise your brain. How many of you like to play chess over here? Well, I love to play chess. Anyone else who likes to play chess over here? Constrained coding competition against other coders. Correct, Devansh Surana. Thank you. So, even chess is a mind sport, and competitive coding is another form of mind sport. Yeah, even I love to play chess, everyone. So, just like chess, even competitive coding will help exercise your brain. Now, let's see how. What's the competitive aspect for it? Well, as some of you correctly mentioned, competitive aspect means that we are competing or we are imposing competition in coding. But how exactly are we doing that? Well, don't worry. It's not based on how fast you type. It's simply about your algorithm, the approach that you're using to solve a problem. Well, for any given problem, it can be solved in more than one way. Like you might solve the problem in one way, your friend might take another approach to solve that problem. These are nothing but different algorithms that you'll be applying to solve the same problem. And these different algorithms might have different running times. The time it takes to execute, let's say your algorithm takes 1 second to execute, your friend's algorithm takes 1.5 seconds to execute. These are nothing but the running times of your problem. And this is the main aspect in which competition comes in. Another important thing is the space that your code is occupying. But when we talk about competitive aspect, we majorly focus on the time it's taking to compute. How's your code judged? So I just mentioned that your code will be competitive on basis of how much space it's taking or how much time it's taking to run. Well, that's the main factor on which your code will be judged. Another important thing to notice over here is the test cases that will be taken for your program. So on any platform that you do competitive coding or anywhere that you do this coding, there'll be different test cases or sample inputs that the compiler will take for you, beginning from, let's say, very simple 1 or 2 input, going up to very large or very big numbers or very difficult inputs, because this is how we're providing a very vast range for testing your code. And depending upon how fast or how good your algorithm can run in all these different environments for all these different inputs, your code will be judged. We'll talk about this more later in the section. Stages involved in solving. I'm sure a lot of us must have been doing coding from a high school or maybe even before 11th and 12th. But if not, don't worry. Stages involved when we are doing a coding problem is very simple. Obviously, the first step would be understanding the question. We should not be in a hurry to just read the question and start typing out the answer, because we have to understand the question, get to the depth of it first. Then we'll be devising an algorithm or an approach to solve that problem. After that, we go ahead and implement that approach in any language that we are using to solve, let's say C or C++ or Java or Python. Simply converting that algorithm or your logic into the code is the implementation. And finally, that some of us are very scared of, debug. See, getting errors in coding is a very common thing. In fact, not getting errors is an uncommon thing. And trust me, it is very common that we spend hours and hours on debugging and still don't get to the conclusion or get to the solution. But debugging is the best part of coding because we all learn from mistakes, right? And errors is the mistake by which compiler or the program is telling you that this is the error. By throwing errors, it's asking you to correct your mistakes. So never be afraid to debug. Questions in competitive coding contests often include the applications or a combination of these. Don't worry, this is not something that you have to go ahead and memorize that, okay, is my question on number theory or is my question on graph theory? No, you're not expected to do any of that. This is simply a category for a rough idea or to tell you that on what topics or on what categories the questions can come. Let's say, for example, string analysis. Simple question like taking two strings and concatenating them is also a question on string analysis. Well, when you go for competitive coding contests, there's going to be different combinations of these categories, or maybe two or more than two, which will be used to give a nice problem for you to solve. Well, this is something that most of us come across when we go ahead with debugging or writing a problem. Has happened with me a lot. Okay, so we just understood what competitive coding is. Now let us start with a little technicalities. Time complexity. Any of you have any idea about what time complexity is? It's the time which our code takes to run. Precisely. Karthik, you want to answer?
The code completion.
Time for the completion. Okay. So there's a little trick over here. When we write a problem or when we write a code for any question, the time taken for that question to run, let's say 1.2 seconds, is not the time complexity, but it is the running time or the execution time of your problem. Now, how is it different from time complexity? Well, time complexity is something which is basically a function or something that can on average, like how much time will your program take to run based on any input. Like for any example that you are taking for solving any problem, that for the running time for that problem, let's say 1 second or 1.1 second, is restricted to that very problem because it depends on the input again, right? If you have a simple input, it might take less time to run. For a very large or complicated input, it might take more time to run. So time complexity is something that determines determines the function on an average, or worst case or best case, on which the time taken for a problem will be analyzed, like for execution. If you did not understand much of this for now, let us get to the next topic, which is asymptotic notations, which is a clear representation or explanation for how time complexity works. So, asymptotic notation. Well, okay, Nirav, you want me to repeat? Okay, Soham, could you go back to the previous slide? Okay, so time complexity, most of us confuse time complexity with the execution time. Like, for example, if you have a program which takes 1 second to run, that is not the time complexity of a problem. That is simply the execution or the running time for that particular problem. Time complexity is a function which can determine the execution time for any input. Like for it's a function with, like we've read about functions, right? Let's say there's a function n square plus n, where n will be the input. So time complexity's function determines the running time for your problem as a whole and not restricted to one particular question or one particular problem. Let's get to the next topic, which could make this even more clear. Asymptotic notation. Now, time complexity is basically determined by three main notations that we use, which are big O notations, theta notations, and omega notations. Well, if you want to know what exactly asymptotic notations are, they are nothing but mathematical notations or computational notation which will help to explain your time complexity using a formula or using something which makes it clear with respect to the time your problem is taking to execute. Let's get to the first notation over here, which is the big O notation or the worst case analysis. Now, I'll just ask you a quick question over here. If the first notation is about the worst case analysis, what could the second and third notation be? Any guesses? Best case, correct. Average case, yes, correct. Fastic. So the three cases that we'll be analyzing over here are the worst case, best case, and the average case analysis. So let's begin with the first, which is the big O notation or the worst case analysis, which is the most important one, because when we go out in the commercial world or when we are solving problems on a platform, worst case analysis is the best thing or the best measure for how efficient your problem is. There's an English phrase that you all must have heard, that you know how strong a man is by testing him in his worst situation. That's exactly what's applicable for coding as well. So, big O notation. There's a complicated formula in front of you, which will be broken down bit by me. F of n equal to big O of g of n if f of n is less than or equal to c into g of n, and n is more than or equal to a number n naught. And over here, c and n naught are constants. If you did not understand this at all till now, don't worry, I'll get to it. Well, before I move on to the next page, which is having an example to explain this formula in a very simple and a very good way, let's get to the graph that you can see over here. In the graph, you can see that the y-axis is representing the time that the problem is taking, and the x-axis is a function. Well, there are two curves on the graph which are intersecting at 2 or 3 points before the x coordinate equal to n naught, and not intersecting at any point after x coordinate is n naught. Well, this is the n naught that we're talking about in the formula. If you break down the formula and try to relate it with the graph, you will be able to notice that we mean that for every value which is for every x coordinate, or for every value of n which is greater than n naught, both the graphs are increasing, but they're never going to intersect. And for any value which is less than n naught, the graph would be random. Let's understand this better with the example. Okay, so let us take an example of a function which is, say, 4n square plus 5n plus 3. If we take another term, let's say 5n square, and if the value of n is greater than or equal to 6, okay, so let's go ahead with substituting the value of n in the given equation. When you substitute the value of n equal to 1, you'll get a value of 4 into 1 plus 5 plus 3, which is 12. Now, when you substitute the same value 1 in the other term, which is 5 into n square, you'll get a value of 5 into 1 square, which is nothing but 5. If you go ahead and do the substitution of the values of n beginning from 1 for 2, for 3, for 4, for 5, you will notice that the value of the first expression, which is f of n over here, which is 4n square plus 5n plus 3, is always greater than the value on the right side, which is 5n square. Now, this is going to happen until the value of n is equal to 5. But when you go ahead and substitute the value of n equal to 6, you will get a value of the function 4n square plus 5n plus 3 less than the value of the function 5n square. This is precisely what our formula was also telling us. Look at the third last sentence on the slide in front of you. You have g of n equal to 5n square for n greater than or equal to 6, where by this we mean that, as I told you, as we move till the value of n equal to 5, we will see a consistency where the value of the function is greater than 5n square. But just as we reach the value of n equal to 6 and we move ahead with n equal to 7, n equal to 8, it will get reversed, which means the value of the function will always be less than the value of 5n square. So I'm going to go back to the graph for a second. What I just said could again be related with this graph. So over here in the example that I just explained, can any of you guess what the value of n naught is? Relating with the example I just gave?
6.
Correct. Thank you, Karthik. So the value of n naught in this example is 6, because we notice the pattern that after n equal to 6, the graph never intersects, and the value of the function 5 into n squared. So over here, the value of c is 5, and g of n is n squared. So the value of 5n squared is always greater than the function that we took for every value of n greater than 5, greater than equal to 6. In this case, if any of you did not understand anything or want me to repeat any part of it, please tell me. Any doubts, anyone?
How did you get the function 5n square?
Okay. So see, whenever we look at the question, we have 4n square plus 5n plus 3. So when you go ahead determining the term for which you like g of n, for which you can in terms of which you can express the time complexity, you always focus on the biggest term in your equation. Like in this example, we have 4n square plus 5n plus 3. Out of all these terms, which term do you think will impact the equation the most? 4n square, right? Because 4n
Yeah.
square is the biggest term among 4n square and 5n and 3. So the best example, or the best try that you first take to find your time complexity equation is by taking the term which impacts the equation as a whole the most. This algorithm can also be applied to find other time complexities, such as O of n cube, O of n raised to 4, and so on. With this example, we get the value of f of n function, or the time complexity, equal to big O of n square. We can omit the value of constant 5, because our term will always depend on n square when we go on to a big number. Let's say when we move on to value of n equal to 1000 or 1 lakh or 10 raised to 10, 5 is very small in front of that, isn't it? Do any of you want me to repeat any part of the algorithm? If you've not understood till now and you're shy to ask, don't worry. The next example is on the best case analysis, which is again very similar to it, but I'll explain it again so that in case you did not understand the worst case, you will understand the best case. So, the second notation, the omega notation or the best case analysis. Now, what is happening over here? Any guesses with respect to how it could be different from worst case, the main difference?
The reverse of the worst case scenario.
Exactly. It's
Like
going to be reverse of the worst case scenario. Like in the best case, in the worst case scenario, we had the curve which was always increasing and which was always above our function f of n. But over here, we can see a curve c into g of n, which is the time complexity curve, always less than the function f of n after a point n naught. Okay, let's get to it in a very simplified manner. Best case analysis is going to give you an analysis of a time complexity in terms of which your problem is never going to have a time complexity less than the time that your best case is taking. I have a very good example to explain this to you in a better manner. Let's say we have an array in which we have to find a number. Let's say we have to find the number 5 in an array of 10 elements. Okay. As soon as you find the number 10, you can break, as soon as you find the number 1 in that array, you can break out of the array and your problem ends over there. And you're using a loop to do the same. So if you have the number 1 situated on the first position itself, this is nothing but the best case, right? Because you are saved from all the other iterations and all the other loops that you would have gone through otherwise if your number was not on the first index. With respect to this example, what do you think the worst case would be? Why should the number be so that this is the worst case for your example? Any guesses? Are you guys on the same page as me? Last position, correct, Nirav. So if the value or if the number 1 is on the last index of the array, which is the 10th index, you have to go through all the other indexes beginning from 0, 1, 2, 3, and go on up till the last because you never find the number 1 before that, right? So in this case, your program is going to take the maximum time for execution because you're not saved from any iteration. So that is the worst case. So that is exactly what the best case and the worst case analysis are doing, because the worst case is giving you the maximum time your problem can take. If your number is at the last position, it's going to take maximum time, right? And your best case is giving the minimum time, which is the first index 1. So index 0, I mean. So in that case, your problem will take the least time to execute. And all the other cases lies in between 0 and the last index. I'm sorry. Do you have a doubt, Dheeraj Kumar? Okay, cool. So let's get to the formula again. Over here, we have f of n equal to omega of g of n. And f of n is greater than or equal to c into g of n, where again, n is always greater than or equal to n naught, and c and n naught are again constants. You can relate this with the graph. As you can see that before the value of n equal to n naught, the graph is haphazard and it's always intersecting at more than 0. It could intersect at more than 1 point, it could not intersect. But the uniformity after n naught is that it never intersects. And the function is always going to take a time more than the best case or the time complexity in the best case scenario, which is c into g of n. Now, let us see an example to understand the same again. Okay, so the example over here is f of n equal to 5 into n square plus 2n plus 5. The value of the function is greater than or equal to 4n square for all the values of n greater than or equal to 1. Look at the table in front of you. When you have the value of n beginning from 1 going up to 2, 3, 4, 5, 6, for each of these values, when you substitute n in your function, which is 5n square plus 2n plus 5 in the middle column, you have n for n equal to 1, you get the value of function equal to 5 into 1 plus 2 plus 5, which is 12. For n equal to 2, you get 5 into 4 plus 2 into 2 plus 5, which is 29, and so on. And similarly, if you substitute the value of n equal to 1, 2, 3, 4, 5, and so on for 4n square, you get the value of 4, 16, 36, 64, 100, and so on. Now, what is the similarity that you can see in the entire table over here, or a pattern that you can see when you compare the second and third column? Which function gives us analysis, f of n or g of n? Okay, so Nirav, f of n is the function which is the function for the time complexity, and the entire function for time complexity. But when we want it in terms of the notation that we're using, Let's say in the worst case analysis, we had big O of n. Over here, we have omega. In those cases, we are using the term from the function which is having the maximum impact in determining the entire time for the running time of the program or any problem. Okay, so let's get back to our table. The common pattern that we can see over here is the value of the function f of n is always greater than 4n square. And in the previous example, we had the value always, where we had the value similarity or pattern after the value of n equal to 6. But over here, we have the similarity or a pattern from n equal to 1 itself, which means that your graph is never going to intersect, not even before n naught, because the value of the function is always more than 4n square, which means your best case is always going to be below the curve of your function. When you compare it, again, come to the lower part of your slide, we have g of n equal to 4n square for n greater than or equal to 1, exactly what I said over here. And therefore, we have f of n equal to omega of n square. This algorithm is again applicable for other values as well, to find omega of n, omega of log n, omega of 1, and so on. Did you all understand? Okay, so over here, as I said in the previous doubt as well, that when we are taking a term which has the maximum impact when it comes to time complexity, like for the function of 5n squared plus 2n plus 5, when you are going for the worst case analysis, since n square is the term which could give the highest value or which could affect the term the most. Okay, let's understand this with an example. Let's say you have a value of n equal to say 1000. Okay, so you will get the first term equal to 5 into 1000 square plus 2 into 1000 plus 5. So your last term is 5, your second term would be 2000, and your first term would be 5 into 1000 raised to 2, which is the square of 1000. So when you make a comparison, your first term is having a value which is much greater than your second and third terms, right? So that is how you get the term which you have to use for analysis of the best case and the worst case both. And you could omit when you are representing it with the asymptotic notations, you omit the value of constant. Like in the previous case, you had the constant 5, and over here you have the constant 4, which you omit when you're going for your algorithm. The next case, thank you. So the next case, which is the asymptotic notations, we have the average case analysis. By now, if you understood the worst case and the best case analysis, I'm sure that you must have had a clear or even a rough idea of the average case analysis. But if you have any residual doubts left, it will be clear after this one. So the theta notation or the average case analysis, we have the function. I'll just read out the formula first. F of n equal to theta of g of n if c1 into g of n is less than or equal to f of n less than or equal to c2 into g of n, where n is greater than or equal to n naught and c1, c2, and n naught are constants. What is the similarity again that you can see between the three cases? If you carefully notice, this case is doing nothing but combining your worst and best case analysis. Okay, quick question over here. Out of the worst case and the best case analysis, which of them was giving you an upper bound for your problem? Or in the sense, the maximum time your problem can take? The worst case or the best case? Worst, correct, Devansh. Okay. Similarly, if the worst case was the upper bound, we have the lower bound, which will be the best case. So in average case, we will combine both the worst case and the best case to get a function which will always be between the curves of the best and the worst after a value n not again. So as you can see in the graph, when we represent f of n in terms of theta of g of n, we get the value of f of n always lying between the two increasing curves, which is c2 of g of n and c1 of g of n. So out of c2 of g of n and c1 of g of n, your worst curve, as your friends correctly answered, is the c2 of g of n, which will be the upper bound, and the lower bound, which is c1 of g of n, which will be the best case. So your function f of n is always going to be between these two curves. Again, I have an example for you. So let us consider an example where the running time is 3n square plus 2n plus 1. You can relate it again in the same manner that you did for the worst case and the best case, where you have the function given 3n square plus 2n plus 1 and increasing from 1. You have the worst case analysis based on the term 4n square, and you have the best case analysis based on the term 2n square. You find the similarity, you find the value of n naught by taking the value starting from n equal to 1. And in this example, you will see that after the value of n is equal to or more than 3, The value of the function is always between the worst and the best case, as you can see in this example. So you can go ahead, take this as your homework, try to sort this out, and if not, you can always get back to us with your doubts. So this brings us to an end of asymptotic notations. The next slide is a very good comparison graph over here. You can see the three comparisons very clearly over here. I hope this will clear all the remaining doubts that you might have had. The first case is having a worst case analysis, which means the yellow portion represents the running time for your algorithm. So in the first case or the worst case, your time will be always less than the curve C of G of n, which is nothing but the worst curve, or the curve which is giving the worst or the maximum time for your problem. Similarly, the second graph, which is the omega graph, is showing you that the minimum time is always C of G of n, C into G of n, and your problem is always going to take a time more than this curve. And in the third curve, we are combining these two curves to get the yellow area, which is always between the best case and the worst case. This is same as the array example I took, that if you have the number at the first index itself, it is nothing but the second graph, which is the best case, that your problem is always going to take more time than it takes to find the number at the first position. Just the opposite for worst case, that if your number is at the last position, your problem is going to take always less than or equal to time than the last position. And the middle position, which is always going to be between the first index and the last index, because that's the three possibilities you have to find the number, right? I'm glad you all were very interactive and asked me questions. If you still have any doubts, you could ask me or we could get back to it at the end of the session. So for now, I hand over the session to my friend Soham, who will be taking it from here.
Uh, Hello, I'm Soham Mittal, and I'm gonna continue the session from here. As my colleague Srishti taught you guys about asymptotic notations, let's see how to apply them in our programs. But to do so, first we would need to figure out the running time of our algorithm. So here I have a very simple algorithm, a simple 3-line one, and we'll try to figure out its running time. So the first line, we are just initializing a variable named sum to 0. So let's assume its cost was C1. And I've written 1 in times column because this statement is only executing once. We are only initializing it once. Coming to the second line, there's a for loop which runs n times from I equals 1 to n. So let its cost be C2, and I've written n in the times column because it's gonna run n times. And in the third line, there's a simple addition happening. Let its cost be C3, and it's also happening n times because it's inside the for loop. So now the running time of a algorithm is nothing uh, more than the sum of all these costs. So let's sum them up. You will get C1 plus C2 into n plus C3 into n. Now just grouping terms together, we get n into C2 plus C3 plus C1. Now you will see that we actually don't care about the constants as much. You must have noticed in the best and worst case analysis slides too that in the end we ignore constants. Our time complexities don't ignore constants. So we can replace these constants with any other. So let's just term C2 plus C3 as A and C1 as B. We get a final of A into n plus B. This is the form of a running time of our algorithm. Now let's see how to convert this into our asymptotic notation. So first of all, a point to note, we would be only talking in terms of big O notation, that is the worst case notation, because that's actually the most important in competitive coding. We want to know how our program performs in the worst case. It should perform good enough in the worst case. That's why we always care about the worst case notation. So let's go through the steps. The first step is to find the order of growth, that is the time complexity. We should only consider the fastest growing term or the leading term. So let's take an example, an square plus bn plus c. So here we have our terms as c, b into n, and a into n square. The fastest growing term among these is obviously a of n square, a into n square. That will grow the fastest as the value of n grows. So we'll only consider that and ignore the rest. So we are left with a into n square. Now we ignore constants. our time complexities don't care about constants. So we'll ignore the constant a to be only left with a variable, that is n square. So our time complexity, specifically the worst case, big O time complexity, here becomes O of n square. If you guys have any doubts, I'll be happy to take them. I assume all of you understood. So we'll move on to the next topic. And so when you don't evaluate the time complexity of your program very well, you might get this error in a lot of problems. That is time limit exceeded. That means your program exceeded the time limit of the program. Usually you'll see a 1 or 2 second time limit. So you can see that Hulk is happy with it, but you should not. You should always strive to get a lower time than the time limit. Okay. So we have been talking about time complexities now. There are many of those, but how to compare between them? Like which one is good, which one is not good? How to compare between two programs with different time complexities? So here's a very nice infographic which will help you compare time complexities. On the bottom right, you can see O of 1 and O of log n. These are the best time complexities. These are any programmer's dream. Moving upwards, you can see O of n being slightly worse, and O of n log n being worse off, and so for n square 2 to the power n factorial. So just a quick question. Can any one of you tell me which is the best and which is the worst time complexity shown in this graph? Yeah, Devan says worst is n factorial and best is O of 1, which is absolutely correct. Thank you for the answer. And these are nothing other than the plotting of the same graphs. Like let's take O of n square. So you can see this curve. You'll get the same curve if you plot y equals n square. It's the same curve. So you can even make them on your copy on your own. So let's move on to some time complexity examples. So the first one that I'll be taking is the best time complexity that we discussed, O of 1. Let's just take a simple loop which runs C a constant amount of times. It goes from I equals 1 to I equals C. So let's try to think in real world terms instead of programming terms to make it a bit simpler. Let's just assume C has 5. Let's say the loop runs 5 times and we have 5 apples. So basically what we have to do is we have to go from the first apple to the last, one step at a time. Very easy, it will take 5 steps. So let's say it was C was some other value, it would have taken 3 steps in total. Now our program's running time does not depend on any variable. We only have a constant C. And we ignore constants, right? So ignoring the constant, we are only left with O of 1. That is a constant time complexity. That's the best case. Uh, any one of you has any doubt? I'll be happy to answer them. Okay, assuming you guys understood, let's move on to our next example, which is O of n. So let's analyze another loop. This loop is also going from I equals 1 to I equals n. However, it's jumping C steps at a time. C is being added to I every time. So let's just imagine another set of apples, n apples to be precise. And now we want to go from the first to the nth apple, jumping C steps at a time. So there will be a total of n by C operations, or the loop will run a total of n by C times. Now again, we ignore constants, right? So we'll ignore the constant C and we'll be just left with n, our variable. So the time complexity will be O of n. Now let's move on to our next example, which is O of n square. A slightly more difficult one because we have now two loops inside one inside another. However, don't worry, with our apples, we'll be able to figure it out very quickly. So you can see the outer loop, the I loop, is the same as our last example, going from I equals 1 to n, jumping C steps at a time. So we know from the last analysis, it will run n by C times. However, every time our outer loop runs, our inner loop runs n times. going from j equals 1 to n. We can see this as a matrix of apples. So first, we'll go through the first row, jumping c steps at a time. Then the second row, jumping c steps at a time, all the way till the nth row, again jumping c steps at a time. So for one row, we need n by c operations, and we have a total of n rows. So we get n square by c. Now again, we don't care about the constants, so we'll ignore c, and we'll be left with O of n square as our time complexity. If you guys have any doubts regarding O of n or O of n square, you can type it in the chat box or speak up. I'll be happy to answer. Okay, assuming you guys understood, let's move on to our next example. So our next example is log of n time complexity. Now this can be slightly complicated. However, I'll make it simple for you. Don't worry. We'll see a loop, a very similar loop, I going from 1 to n. The only difference is I is not being added to, instead being multiplied by c every time. So let's just observe a few things in the loop. In the start, the value of I is 1. After one iteration, being multiplied by c, value of I will become c. Then after another iteration, being multiplied by c again, the value of I will become c square. Similarly, let's say the loop runs 5 times. In the end, the value of I will become c to the power 5. Now, with this observation, let's just assume the loop ran a total of x times. Let's just assume. What's the harm? So, if the loop ran x times, in the end, we know the value of I would have been c to the power x. And the condition for the loop to stop is the value of I should be less than equals to n, right? So, c to the power x less than equals to n, and taking logarithm both sides. I hope you guys remember logarithm from high school. We get power of x to the multiplication, x into log c is less than equals to log n, and c is a constant, so log of c will also be a constant. Again, we don't care about constants, so we can ignore those. We ignore the log c, we get x less than equals log n. This means x will be always less than or equals to log n, so x will be in the worst case equal to log n. Remember, x is the number of times our loop runs, that is our number of operations. So the number of operations in worst case becomes log n. And remember, we were all the time talking about big O notation or the worst case. So we get our time complexity as big O of log n. If you guys have any doubts, I'll be happy to answer them regarding log n time complexity. Yes, Devansh, you very correctly pointed out that if C is between 0 and 1, it would result in an infinite loop. However, we can assume that it is all in integers. A pretty interesting observation though. Okay, I'll move on to our next topic after log and time complexity. And let's do an exercise. Let's see how much you guys have learned, and let's put it to test with a simple example. I'll give you a minute, try to figure out its time complexity, and you can type it in chat or speak up. I see a few people have already answered n square. I'll wait for 10 more seconds. Okay, a lot of people are answering n square. Okay, a few people have started answering O of 1 and O of n also. Okay, let's see. Okay, I'll give you guys a hint. I'll tell you the answer, but now you got to give me the reasoning for it. So I tell you the answer that the time complexity is O of n. Now, can someone give me the reasoning why it's O of n? Okay, Nirav has explained that the second loop is running only once, which is absolutely correct. I'll explain it. So, we can see the second loop has a break statement inside. So that was the trick actually. What the break statement will do is never let the inner loop run more than once. Whenever the outer loop is running, the outer loop will run a total of n times. But whenever the inner loop will try to run, it will immediately break out after one iteration because of the break statement. So only a total of n iterations will be made, and the time complexity will become O of n and not O of n square. It was nice to see few of you figuring this out and not falling for this trick. Okay, now let's move on to another exercise. Okay, I assure you there is no such trick like the last exercise. I'll give you a minute and you can try to figure out its time complexity. You can type it in the chat box or speak up. Okay, a few people have been saying log n. I'll wait for 10 more seconds and then I'll reveal the answer. Okay, fine. So what is n? Nirav is asking. So n is a variable. You don't need to know its value. It's just a variable. It could be anything. You can assume it's positive. Okay, Akshit has answered n to the power half or root n. Quite interesting. Okay, so I'll tell you guys the answer, and now you guys got to give me the reasoning instead. So I'll tell you that the answer is O of root n. So Akshit had told us the right answer. So can someone from you tell me the reasoning why it's root n? Okay, Nirav is saying it's related to I square, which is correct. Okay, I'll explain. So what's happening is value of I is starting from 1, and every time the loop runs, its value increases by 1 more. So let's say the loop runs a total of 10 times. Value of I in the end will be 1 plus 10. Simple. Now, for the second observation, let's see when the loop will stop. The loop will stop when I into I, that is I square, will be greater than n. That's the stopping condition, when I square will be greater than n. Taking root both sides, we'll get I greater than root n. So the while loop will stop when I is greater than root n. So I will be for the first time, be greater than root n when the loop has run root n times. Because after running root n times, the value of I would have become 1 plus root n, which is just greater than root n. So that's why the time complexity is O of root n. Okay, I'll repeat how it became root n. So see the condition inside the while loop. I square is less than equals n. So that's still when the loop runs. That means the loop will stop when I square is greater than n. Now I square is greater than n is same as I greater than root n. Now what's the smallest number just bigger than root n? Root n plus 1. Really, you can't go much lower than that. So if the value of I becomes root n plus 1, our loop will stop, our program will end. So let's see how much time it takes for the value of I to become root n plus 1. The value of I is starting off with 1, and every iteration it's increasing by 1. So after 10 iterations, it will be 10 plus 1. Similarly, after root n iterations, it will be root n plus 1. So that's how our program will stop after root n iterations. So the time complexity is root n. Okay, I see you guys have understood. I'll move on. Let's see a question now. We have been doing a lot of time complexity, but let's see some actual questions that we'll see in competitive coding competitions. So let's just take up a simple question and try to solve it together. So let's say we have a sequence of n numbers, then how many such sequences will satisfy the two following conditions? As you can see the conditions in front of you, all numbers should be between 0 and 9 inclusive. That means including both 0 and 9. And the sequence should have at least 1 0 and 1 9. So this is the question, and I want you guys to try to guess which concept or what technique, what what are we going to use. If any one of you knows, what do you think we will be using in this question? Okay, Devansh correctly pointed out combinatorics, which is correct. This is the combinatorics question, and we'll be seeing some of it. Okay, let's move on a little and see some sample test cases. That is answers for some inputs. So let's see the left diagram. If the input is 1, that the value of n is 1. That is, our sequence needs to be of length 1. Then the answer would be 0. The sample output is given as 0 because if our sequence must contain at least 1, 0 and 9, it can't be smaller than length of 2. Because to just include 1, 0 and 1, 9, we already reach the length of 2. So we will have no such sequences. Now let's move on to the right diagram. When the input is 2, that is, the length of our sequence should be 2. Now the answer is 2. How so? Because we need to include 0 and 9 at least, and there are two ways to do so: 0, 9 and 9, 0. These are the only two valid sequences because we already have reached length 2. Adding anything more will lead to a greater length. I hope you guys have understood the question. If you still have some doubt in the question, I can answer. Okay, so we'll move on to the concept that will be used, the specific combinatorial concept, that is the inclusion exclusion principle. That's something we'll be using here. Now, many of you might have already learned it in your high school. It's taught through sets usually, and the statement is that the union of two sets is the sum of both sets minus the intersection. Why is it correct? Let's see the diagram. Now, the left set of circles, you can see they are the sum of two sets A and B. And now, when we do the sum of both of these, we actually are counting this area once, however the intersection twice. Why? Because the intersection is part of both the sets A and B. So what we need to do is subtract the intersection once, so that we are counting each area only once. And that's how we get the union of both the sets. So that's why this formula is true. If any one of you hasn't understand the inclusion exclusion principle, you can type it in the chat box. Okay, I assume you guys understood. Let's move on to the solution finally, the final reveal. So the solution. Now, how we'll start is, we'll apply a common theme in competitive programming. Sometimes, if a problem asks you to do X and it's very difficult to do X, what you can do is do the opposite of X. So we'll do the same. We are asked with sequences with at least 1, 0 and 9. It's actually pretty hard to find out because there could be 1, 0, 1, 9, 1, 0, 2, 9, 1, 0, n9, n zeros, m9. So many so many mind-boggling combinations. Instead, we'll make it simple and we'll find all the sequences with no zeros or no nines and subtract them from the total number of sequences to get the same result. So now let's go step by step and start with the total number of sequences. So if we have a sequence of n numbers and each number can be between 0 and 9 inclusive, that means we have 10 options for each number. So if we have 10 options for each of the n numbers, we'll get total 10 to the power n sequences, because all those values get multiplied. The first has 10 options, the second has 10 options, and so on. So we get 10 to the power n sequences. Now, to figure out sequences with no zeros or no nines, let's use the inclusion exclusion principle. Let's divide it into two parts: sequences with no zeros and sequences with no nines. So here I have divided it with A being no zeros and B being no nines. Let's see how we can figure out the number of sequences. Now, the value in the set A is 9 to the power n. Why? Because set A is no zeros. That means out of the 10 options we had for each number, we are eliminating one option, that is, each of those numbers cannot be 0. So we will have 9 options from 1 to 9. So 9 options for each of the n integers, we get 9 to the power n sequences. Very very similar for B. We also had 10 options, but we eliminated one option, that is 9. So we only have 0 to 8, that is 9 options left for each integer. So a total of 9 to the power n sequences. Now coming to their intersection, we want no zeros and no nines. So we are eliminating 2 options out of 10, leaving us with only 8 options per number. So 8 to the power n. Now if any one of you has any problem in how I got those values, 9 to the power n, 9 to the power n, 8 to the power n, you can type it in the chat box or speak up. I'll explain them again. Okay, assuming you guys understood. Now we'll just compile all of them to get the final answer. We take the total number of sequences 10 to the power n and subtract A union B, that is A plus B minus A intersection B, same values we got from the diagram, and just simplify the expression to get the final answer. See how we simplified the whole problem, which has so many mind-boggling combinations, to such a simple formula. So this is a common theme you will find with combinatoric problems. Now, if anyone of you still has a problem with a question or solution, you can ask, or I'll move on. Okay, so let's move on to advantages of competitive coding. Now my friend Shrishti will continue from here.
Oh, a lot of technicalities, right? But I'm sure you found the session interesting till now. Before I move ahead, if any of you have any doubt or you want any of the parts to be repeated by Soham or myself, please let us know. Okay, so we've got a pretty smart audience. So let's move ahead with advantages of competitive coding. Well, since the beginning, we've been seeing what competitive coding is. We saw time complexity, we saw asymptotic notations, we saw examples, we gave you exercises, and then we came to a problem which applies the concepts, right? But why are we doing all this? We should know why we are learning something, right? So a small session where you don't have to use much of your brains, you can relax, get back, and just listen to why we should do competitive coding. So Improve your problem solving ability. I said it's a mind sport, right? Well, it helps exercise your brain. It forces you to think because every new problem out there waiting for you is going to ask you to apply your brain in a different manner. It's going to force you to apply your logic, to use your thinking and find a solution to the problem, hence improving your problem solving ability. Challenge yourself. Well, there are no end to problems. And yeah, before I move ahead, there's a huge takeaway for you at the end of our session when we tell you about the platforms of where you can begin competitive coding. So hang in there. Okay, so challenge yourself. There is no end to problem. You can just go ahead, challenge yourself with the same problem that you solve to solve it in a better manner. Or you can challenge yourself for solving different problems and take, less time to solve different problems. Or you can challenge your friends, like with respect to the problem that you previously solved, you want to solve it again or something like that. But never stop challenging yourself because you're always going to learn or you're always going to improve when you same solve any question, even if it's the same question or a different question again. Gain recognition. Well, who doesn't want recognition? I'm not just talking about recognition in your friends and family members, but when you go ahead, when you solve questions on a platform, you're going to have a name over there too, right? And trust me, being on top of that leaderboard on any platform for the day or for the week, that holds so much importance. And it's a really great feeling to be, recognized by people when you're doing good coding. Ace your placements. Who doesn't want to ace our placements? Well, a lot of us have come over here with the aim that at the end of 4 years, we want to place into a very good company. Let me tell you this, no matter how good you are with your extra activities, with your web development, app development, machine learning skills, coding is always going to be a part of it. Be it interview rounds, be it personal interview or pre-interview rounds, coding is always going to be there to test your skills in terms of your thinking, in terms of how you apply your logic, in terms of how efficient algorithms you write. So even if you start practicing one problem per day, starting today, just imagine you would have solved more than 1,000 problems by the time you sit for your interview, and it's going to help you a lot, trust me. Enjoy. What other motivation do you need when this is something so fun to do and something that's gonna, not just be so beneficial for your career, but you're gonna enjoy doing it. Once you start solving problems, once you get addicted to it, trust me, there's no going back. Even I did not solve much problems when I joined college or when I started doing other stuff. But once I got into competitive coding, there hasn't been one day where I haven't tried my hand on at least one problem. So it's a really fun thing to do, trust me. Here comes the biggest takeaway for you, the platforms. So I'm sure you must be so interested in competitive coding after this session, and you must be willing to, try at least one or two problems before you decide that you want to move ahead further with it or not. So my friend is going to give you some amazing platforms where you can go ahead and begin your trying, testing your skills.
So let's see some platforms now that you might be more interested and actually want to solve some competitive problems where you can do so. So there's some online platforms, also popularly known as online judges, where you can go and solve a lot of these competitive programming problems. So a few of the popular ones such as CodeChef, Hackerrank, HackerEarth, LeetCode, AtCoder, TopCoder, CodeForces are listed. All of these are very good sites, and you can go to any one of those and start practicing even today. And as you can see, maybe the picture on my right, these programs really test your code very thoroughly. So even if there's some small bug or your code is a little bit too slow, you're gonna see a wrong answer or a time limit exceeded. So they really make you write efficient programs. Now let's actually see some and discuss about some of these platforms. CodeChef. So you can find CodeChef at codechef.com, and it hosts 3 monthly competitions. So you can easily compete and test your skills and compare yourself to others. It's most famous for its long challenge, that is a 10-day long challenge, and it's mostly centric towards learning. That is, it gives you ample time to read a problem, think on it, then learn some new stuff that should be applied, and come back and implement it. Also, the problems are from a wide array of categories so that you can learn the most. It also hosts two short contests named Cook Off and Lunchtime, and they're really good too. Now let's move on to our next platform, that is Hackerrank. Now Hackerrank is actually also very good for practice. You can find a lot of practice and standard questions on Hackerrank. Some of its unique things are language tracks. That is, if you feel that the language you do competitive coding in, be it C++, Python, or Java, or any else, you can find the language tracks. That is, you can learn more about that language and what functions are used in competitive coding mostly, and learn those. Other than that, it also offers data structures and algorithm tracks. That is, you can strengthen your DS or algo skills perfectly there. Now let's move on to another platform, Hacker Earth. So Hacker Earth is also very good for practice. It has a lot of practice questions. One of the most amazing features of Hacker Earth is a one versus one code arena. It's a very exciting thing. You can just go to the code arena on Hacker Earth and you'll be matched with any random coder from all around the world. And you both will have to compete and try to solve the most test cases in the least time. It's quite exciting. Also, a lot of companies host hackathons on Hacker Earth through which they conduct hiring. So, participating and performing very well in those hackathons on Hacker Earth can actually lead you to get an interview call or even a job offer directly. Now, let's move on to the last platform that we'll be seeing, that is LeetCode. Now, LeetCode is actually quite a popular one for placement preparation. You'll see a lot of people picking it up in the senior years or when placement season is coming. It also hosts weekly and bi-weekly contests to help you test what all you have learned. And also, it has this very nice feature of mock interview preparation where you can take mock interview questions from big companies such as Google, Microsoft, Amazon, etc., and give them in a simulated environment to see how you perform under pressure. So that is all for platforms. And just like how Hello World was probably the starting point of your coding journey, we hope that this Techloop session is the starting point of your competitive coding journey. We hope you guys enjoyed and learned a lot, and we wish you the best of luck for your competitive coding journey.